Okay. Cool. And now. Okay, sweet. Whoever started the recording, thank you so much. Again, sorry about that for last time, but okay, guys. So, I think that he told y'all what's going to be on here. But I will go ahead and say it again. Hold on. I'm trying to figure out how to make this bigger if I can. Hold on. That work? That didn't help. Is like, I can make it bigger, but is that good enough?
That's pretty good.
Okay, cool. Cool. Okay, so the things that are going to be on the test are going to be, you're going to have a name problem. You're going to have a Norton's problem, which is going to use MAME. You're going to have a either an inductor combination problem or a capacitor combination problem. Inductors are easy, so I would assume it's probably going to be capacitor. And then you're going to have a complex admittance problem. So pretty much just what you did on problem set 4. So, said he's not going to give you a pentagram problem, even though I like the pentagram problems. So we're going to do this one first. Actually, what do y'all of those? I'm not going to go over the capacitor combinations. Really, I might go over them a little bit at the end, but I feel like y'all are pretty good on those. Of the 3, Norton's, name, and complex admittances, which one do y'all want me to go over first? Like, which one are y'all the most shaky on that?
I think the words are come.
Okay. All right, we can do Norton's for sure. So, this isn't too bad, but this was an old exam problem. So what we're gonna do, we already have, he already gave IM1, IM2, IM3. So the way that you're going to set up Norton's is always going to be with a MAME. And what I always wrote down in my notes is Norton's equal to voltage sources. Voltage sources and MAME. And same goes the other way. Thevenin's is going to be
Same but reverse.
exactly. But with Norton's, you got to remember you are wanting the end result to be a current source in parallel with a conductance.
Thanks.
Yes. So we can go ahead and start working out this problem. And on this one, this is a thing from the solutions because I didn't have the other one, but really what it would look like is this wouldn't be here. So I hate that that's not white, but you know what? It's fine. So it's just going to be a terminal A and B. And then you would also have to figure out that. Exactly. So this is more what it would look like originally. And then you would figure out, okay, I'm going to add in this voltage source, right? And then you see that now you have another complete mesh. And so this is going to become mesh 2, mesh 3. So let's go ahead. Are y'all?
Well, can we zoom in on
Yeah, just a little bit, the circuit, part in the back.
Yes. I was gonna say, are y'all gonna write it down? Okay, that way y'all can tell me the values, which is great. Okay. But I'll go ahead. You can see that we're going to need to write out equations for I5. And we're going to need to write out an equation for V4. And that's about it for the other equations. We see that I5 is right here. And y'all can't really see that. I5 is right here. So let's go ahead and write out the equation for I5. What is it? Mm-hmm. And I'm going to go ahead and ask you
Shut the fuck up. Got it.
a very kind, let other people answer first. I appreciate it. I know you know. I did the same thing. Let the people in the back answer. But I am 2 minus I am 3. Now, does everybody see why?
Opposite direction.
Exactly. They're going in opposite directions. I'm repeating that for the recording. And yeah. So now I'm gonna crack. You're good. So what is V4 gonna be?
That's what
I am 2 times R4. Alrighty. That is correct. I am 2 times R4, which is equal to just I am 2 because it's 1 ohm, which is super, super easy because these are lovely numbers. So does everybody have the problem written down? Okay, I'm going to scroll down and do the resistive matrix now. So we're going to have its 3 meshes. So it's going to be a 3 by 3, right? 3 by 3 times R I am 1, I am 2, I am 3. So now, yes.
If, like back of the circuit, if he was to make it a little bit more difficult when it comes to I5, like let's say he put I5 between R1 and R2.
Mm-hmm.
Let's say, because I know like on the last test, there was one where it wasn't as easy like
Mhm.
that. So like, let's say he put it between R1 and R2, it would be,
That'd be easier.
yeah, what it, because it goes back down to ground, right? So it'd be R1 times IM1,
Well,
or.
are you talking about I5 or
Yeah, if you
V?
put I5 between that,
That would just be I.
Mhm.
it'd just be IM1, right? Yeah, we'd have to take those components.
I think the other one was using on the test was using main.
Yeah.
Oh, yeah, that's true, yeah, it wasn't.
Because
Yeah,
it was
that's right,
no
yeah.
voltage to ground. I think I semi know what you're talking about.
Mhm.
Currents for the loop are just the currents of the loop combined.
Yeah, it'd be easier for me, but it, right.
Which
Exactly.
would just be IMO.
Yeah, so you can see that this current, if you have components in series, the current is always going to be the same for all of those elements, right? And the opposite goes for voltages, right? So Yeah,
I'm just trying to just think of like, okay, just in case, like,
Mhm.
what if it wasn't that easy, you know, just trying to like, just worst case scenario.
yeah. So,
I don't know, but it's MAME, so it's a lot easier than it was, you know, like.
yeah, and when we go to when we go to the name one, we can look at that for sure. The way that he would make it tricky on one of these problems is if he went from here to here. Like,
Actually, what I was just about to ask you.
so what if he went from,
Where?
so this plus right here and this minus right here? That would be tricky, right? So what would, y'all tell me, what would the voltage, let's call it V question mark. What would V question mark be?
But would it be like,
The voltage at the bottom of R5 is 0, right? Because it's connected to ground.
Yes, and I'm gonna go ahead and say, if you're trying to find voltage or current, never go the way where you have a dependent source.
Gosh.
That's just kind of a,
Go through the resistors and be done with that.
exactly. So, because you're trying to get rid of the dependent part. So you're gonna want to try to go the path that has no dependent places, the simpler way, one would say. So to try to find the voltage from this point here to this point here, you're gonna kind of go in a loop. So what you're doing is you're adding the voltage from here to here, from here to here, and then from here to here. Now, do those polarities that I just drew make sense? Okay, because you're going in this order of adding, because this is the positive and this was the negative. So you want to go from positive to negative in adding those resistance and adding those voltages. So now to add those voltages, we can just say V question mark is equal to V3 plus V4 plus V5. And those numbers are from the resistor numbers.
So it'd be like R3 times IM1 plus R4 times I'm sorry, IM2. And then V5 or R5 times IM2.
Well, is that the only current going through those resistors?
Okay, sorry.
Three and R5 have, the methods, the I.
Exactly.
IM1, the R3, IM2 for, R4.
Right. So,
Just yeah.
and then keep in mind, so I drew the polarities. So that's going to determine which is subtracted. So since I drew this polarity from plus to minus, exactly. So it's going to be 1 times IM2 minus IM1 plus. We already wrote V4, which is just IM2 times 1 plus V5 is going to be, anybody?
IM2 minus IM3.
Mm-hmm. Exactly. 2 times IM2 minus IM3. So if you wanted to give you a really complicated voltage, that's what it would be. Does that seem too bad?
Definitely not too much now.
I'll have to go over it, help, you know, just in case.
All right. No, yeah, it's a good one. I was struggling to find some really good. Mhm. Yeah. And then we can go over, when I go through the name question, I can go through how he would make it complicated with currents. For sure. Well, it would still be with voltages, but how you would solve it. So let's go on to solving for the resistive matrix. Sound good? Any other questions?
Also, just in case,
Go for it.
I guess, so if you, so are you taking the voltages with respect to IM2, or were you just like making your own like pseudo loop?
That is a really good question. So
Because it's like, what happens if like you were to go through like the negative end of a resistor?
yeah, so if you would go through the negative end of the resistor, it's going to be a voltage rise, right?
So you,
Mhm.
but
So
if it's But like, what if you're going like one way and it was, so if you're going with IM2, it's positive. But if you were going like around your loop, you end up going the negative way. You would subtract it because you're taking it with respect to the loop that you're making, not with
So-
respect to IM2.
You're taking it with respect to where the positive and the negative sign is. So you
Okay, so
always,
its polarity stays the same,
yes,
right? Well, so like it stays
Which
the same
polarity?
from the original circuit.
yeah.
Okay.
Yeah.
And then, or the one that you designated in the beginning when you
Mhm.
first started the circuit.
And
And
It-
then whenever you're going around, I'm so sorry. And then
No, you're
whenever you're
fine.
going around, you just follow the same polarity that was already designated.
Mhm.
Okay.
And it's gonna work out the same. So if you designated that since you did IM1 first, you would say, okay, you're going into this negative terminal now because it's IM1 minus IM2. But then it would be negative. So this voltage V3 would end up being negative IM1 minus IM2, which is,
Because IM2 is going through the positive end. But IM1 would be going through the negative end.
mhm.
Right.
No, it was the other way
Or the
around.
other-
So that's with this polarity. So if you determined that this polarity, R3 is going to be a drop from that way. When we have this, we're trying to find this loop. We see that IM2 goes in the negative terminal, or we'll see that the voltage is negative, right? Going up. Because when we're going along this loop from the positive to the negative terminal, we see a negative voltage, but we see negative of IM1 minus IM2 because that's how we determined it originally.
So like whenever you put a negative sign there, you're indicating that is the smaller voltage, and whenever you put the positive, you're saying that's the higher voltage. And that's you kind of guessing what it's gonna be. Whenever you, as long as you keep that assumption of that positive is that one and negative is that one,
Mhm.
your current is either going to come out positive or it's gonna come out negative. Since we know that, thank you, current flows from higher voltage to lower voltage, that's why if it turns out to be a negative voltage, it turns out that what you thought was the smaller voltage is actually the higher voltage, and what you thought was the bigger voltage turned out to be the smaller voltage.
And proof that it's the same is negative IM1 minus IM2 is the exact same as positive IM2 minus IM1.
Thank you.
Sweet. No problem. So we good to go on to the resistive? Sweet. Shut up. Okay. So what's our first diagonal? What's our 1-1? 6. Okay, let's go across. What's the next one? -1. The next one? And that is the exact same as this one, right, guys? Sweet. What is our 2-2 element?
Four.
And 2-3?
Negative.
-2. -2. And our last one? Just 2. Okay. So these are multiplied, and this is equal to, let's do just the general source matrix. So don't plug in the values yet, just what is this going to equal? So instead of doing like what we just say like RM5 mu V4. Okay. So what is the first one going to be?
EG1, EG or EG. That's RM minus mu.
All right. And then the next one? And the last one,
It'd be the voltage source that we added.
which is E naught, right? Okay. So now let's split this up. So when we're doing Thevenins and Nortons, we're always going to split it up into with that too, we need to split it up into independent and dependent and your
What you added in.
E naught, yeah. So we can go ahead, we'll do the independent and dependent first. So we can do equals. Let's do our independent first. What's our independent gonna be? Zero, and we'll put E naught for now. And then plus. Okay,
So what would be the, like, the correct term to call that E naught? Like, cause I know we, like, it's the one that we added on, and it can kind of go with the E naught, but, I'm sorry, the EG. But I know Western wrote it down like two different, it's like it's called two different things. I just forgot the term it's called, like, what you used it, you know?
It's called like an added voltage source maybe, or?
I don't remember.
I mean, it's not that big, I just wondered, like, I just forgot what term. It's called.
It's in my, I wish I brought my notes. I have it written down, but like he labels all these, right? Like
So
EM,
they-
I think it's just EM not. I think that's what it ends up being.
That makes sense.
I don't know if it has like a specific name.
You know, I just realized this is why molten seminar works and why you have to turn off the power supply.
For the second mesh loop, for the sources, you put mu v5, because that's just mu v4.
Yep. So this is what I said. E naught. We already did this. I'm just gonna go ahead and separate them, right? And then we have our dependent one. Do y'all want to go ahead and plug in I5 and V4, or do y'all want to do it one step at a time?
Go ahead, plug it in.
Okay, sweet. So what's the first line gonna be?
It sounds like a sheet.
And then what?
I'm
Five,
two.
seven. 5 and 2.
Like two. Alrighty. And then the next one?
5 and 2.
And 0, right? All right. Now we're gonna separate this into basically resistive elements times your IM matrix, right? So I'm gonna go ahead and multiply this times IM1, IM2, IM3 times, oh, that's terrible. That's, you know what, we're gonna go with it. It's fine. So how many I1s are in the first one? Yep. And then IM2s? Yeah, -3. And IM3s. -2. All right, next row. And 0, 0, 0. Easy. Easy peasy.
And that's the back of the tongue.
Hmm?
So that's the back row talking.
All right, and so now we have this, we have our EMD, I'll label them, and then R and I. So now what we're gonna do is we're gonna subtract EMD from RMI. Two. So, y'all see this? Yeah. So what's that gonna be?
Positive two, positive, two.
Two.
I guess it's negative one.
-1,
Yeah, 5, 2.
1,
It's 7, 2.
0, -2.
Two.
times IM1, IM2, and IM3 is equal to our 16, 0, plus 0, 0, 1. All right. This is our I and our E not. Okay. So now what do we do?
Find what the current is and you find what the resistance, the equivalent resistance is.
Mhm.
And so to find the Norton's equivalent, you turn off E naught and just solve the circuit with your EMI.
Mhm. For the source.
For the,
With J and.
well, so what would the IM3 would be what your Norton equivalent is.
Exactly. So, and I always got it mixed up whenever I was doing this originally, but the way you can think about it is you're turning off E naught. You can't see that. I was trying to cover up my computer screen. It doesn't work that way. You turn off your E naught because you want to find the current. Exactly. So with E naught turned off, you just have a short circuit and it just becomes IM3, like he said. And then the opposite to find the conductance, if you have your this turned off, right? You just have your source and you're finding the resistance. This becomes everything past here becomes like basically a resistive and you're just condensing it down and finding what the
You know, whenever Turner, like, in the 1106 lab says like, okay, before you measure resistance, you have to turn off your power supply. That's because your multimeter is literally that negative positive 1 volt that it's going to add to it. And if you measure with both sources on, you get a very inaccurate resistance measurement. That's why whenever you're thinking of when measuring or when going for the resistance part, you turn off your independent source, but leave E0 on. But whenever you're measuring voltage, the multimeter doesn't add any voltage like E0. There's no E0, it just sorts the two together and then reads the voltages between the two. And that's how you can kind of think of turn off turn off E0 first to find your voltages, and then turn off EG to then find your resistances.
So it explains why multi-sim doesn't work when I check for the answers on current.
exactly.
Yes.
You have to break the circuit first. Yes.
I just realized this 2 minutes ago.
Very nice. We love review realizations. Okay, so let's find our J Norton's is equal to. Do y'all want to just go ahead or is equal to E naught equal to 0, which is equal to. Y'all want to go ahead and solve that in your calculators.
Assuming I did mine right, I got 3.42.
I got that too.
All right. I am gonna check later, but that sounds right. Can you say those numbers again?
Yeah, it's 3.42,
3.42.
negative 1.14, and also negative 1.1.
All right. And so now we know that this is our IM3, which is the value of our J naught. So, J naught,
The JN part, he uses the line, like JN, then line, there equals, you just same. You just have JN equals.
JN and E naught equals 0.
Yeah.
Notation, whatever.
I just. It gets more important in circuits too.
It does get more important in circuits too. Negative 1.14, and this is amps, right?
Yes.
Sweet. So there's your JN. And now let's find our G. GN is equal at EMI equal to 0. What y'all got?
I got, assuming we put it in right. 0.07, negative 0.35, and 0.14.
I got it.
That's what I
You
got.
got it too?
This?
0.07, negative 0.35.
Oh.
That's good.
Okay, cool. So again, it's this bottom one, right? So have our Norton's equal to 1, 4. I think that's
When we like, I guess like the, that could be GN over E naught, right?
Yeah.
Yeah,
Because
like, I mean, I don't think we'd ever have a time where we use like 5 or 6. I don't know if it's ever happened, before, like, in circuits too, or like,
Well,
but I mean, it's, because I know Russell said that if you were to, you could do like 10.
yeah,
Or,
yeah,
because it doesn't make sense.
and the reason is, right, we have our V equals IR. I always write it out every time. And right now we're dividing current by voltage. So exactly. That's terrible. So that's how you know we're actually taking this 0.14 divided by E naught, which is the same as conductance.
Wait, I'm sorry, Keith, because I know Russell explained it,
Mhm.
but I forgot how the second part gives you your conductance.
Yeah, so we solved for this is in amps, this is current. So right now we're using this, right? This and this. We're dividing the current by our voltage, which is our
The
E naught.
resistance.
There, yeah. So I over V, which is what we just did, is equal to conductance. And so that's how we get that.
if you want to mathematically prove it, you can also say, so V equals IR is a linear relationship. So if you take the derivative, R is a constant, like if you take the derivative of, current, wait, no, of R, then the I disappears. And that means that, your derivative is going to be R. So that means that for any value of V, it'll give you some value of I, but R will always be a constant. So you can choose 10 volts, 5 volts, 3 volts. It'll give you corresponding 5 amps, 2 amps, 1 amp or whatever, but your R will always stay the same.
Thank you for our lovely math lessons, David.
That'd be.
That's not. So, and then we're gonna come back up here. And I would appreciate it, and Russell would also probably appreciate it if you draw it back out. So we have our, I know my values are terrible.
Well, since we got a negative J and then zeros actually going down, right?
Yeah, if you want it to be positive, you can also just have it point up and just have the negative amps.
So good.
Either works, but I'll go ahead, like you said, do that. I immediately forgot what they are.
1.14 and 0.14.
You could also make it really fancy and say switch A and B.
Please don't. please don't switch the terminals. Okay, so. Cause yeah, I might catch it, but I also might not. So, how do y'all feel about that? Does anybody have any questions?
That was good.
People online, how are y'all doing?
Or the team group.
All right, good stuff. This is how professors feel whenever nobody answers them.
The metaverse.
Okay, so let's do, y'all said you wanted to do the complex emittance one?
Yes.
I don't have a great problem. I was looking, whenever I was in there all stressed, I was trying to find a good complex emittance problem that y'all hadn't seen. But how did everybody feel about the problem set today?
Yeah, honestly, it wasn't as bad.
Okay. A lot of, I think, the complex emittance stuff is making sure you have your conversions to phasor right, making sure you're able to do rectangular to polar, making sure. Fair enough. Thank you. And yeah, all of it's really just calculator stuff. And so I'm going to go over this, and I'm also just going to kind of try to drill in, okay, here's what to do. And then at the end, I'm going to try to figure out a way to record a couple calculator things, because calculators are hard to use, and I totally understand it. I had to come in and ask for help figuring out how to get the polar angle from the like list of functions in the calculator, making sure you have your settings all right. And so we can go over that in a little bit. But is anybody saying anything? I want to make sure nobody's sending me things in
Good chat.
the Discord. Okay. Yeah, he said eh.
Who's that?
Last name of Dixon. Can't see the full name. But it's all good. But yeah. But okay. Let's talk about time domain. So this is in time domain, right, guys? Oh, thank you.
You zoom in
Thank
to the
you.
big race while we're writing it.
Yeah. This is also in time domain, but we need to remember that it's sine, not cosine. But the way it is you can always think about this in terms of polar. So time domain and polar go hand in hand. And remember, polar is a angle of essentially phi. And this is going to be your A, and this is obviously your angle. So the only two really important pieces of information for the actual phasor, or yeah, the phasor version of the voltage is this guy right here and this guy right here. And your omega is useful for your capacitor and inductor conversions. Right? Because we're going to do either Z, which this one is going to use Z's. Go away. Stop it. I need you to stop. Sorry. So your Z for your capacitor. What's your Z for your capacitor?
So the
Negative
capacitor is
Or
Negative
negative J over omega C.
All right. And I'm going to go ahead and write it 1 over j omega c, which is equal to negative j over omega c. I personally like just doing 1 over j omega c because I remember that all of it's in the denominator for capacitors and all of it's in the numerator for inductors. And I have a habit of forgetting the negative whenever I do it like this.
So, but whenever you do that, you're gonna get the same thing.
Exactly, because 1 over j is just equal to negative j, and that's why. And then z for an inductor, this is capacitor, is equal to
positive J omega.
j omega L. Sweet.
See what HEG was.
Yes. That's better. I can also write this is A, and this is omega T. So what is our phase angle for our EG? Exactly. So this is
And
EG hat. It's going to be 10, 0, which is equal to a lovely, lovely number of 10. We love to see it. So let's go ahead. How do y'all want to solve this problem? You do have 3 meshes.
voltage across it times the impedance, so if we make
So
I'm 1, I'm 2, I'm 3, I'm 3 times the impedance gives us voltage.
That does work. That is
So
far more
back-
complicated.
Pass backwards.
Yeah, you can do voltage divider.
Dumbass, okay.
No, you're good.
L, the impedance for L and impedance for R1 into 1, and we can combine the impedance for R2 and
Yeah.
capacitor into 1. And the
Yeah.
voltage across the branches of R2 and the capacitor are gonna be the same, right?
Mhm.
Cool.
Exactly. Very nice. I don't know if we still have them, but we had stickers for these. Would you like a sticker?
My favorite.
Oh, where did it go? Dang it. I think HKN has some stickers. I will see if I can get some stickers. So, like you said, do you want to, if you combine these two and you combine these two, how are you going to combine them?
Well, the capacitor and the resistor would be like, those would be series. I guess you'd add them up like resistance series, and then when it comes to the top portion, those would act like parallel resistance.
Mhm.
So it would be for the top, yeah, you could just start.
Yeah, so you can either do that because Z, your impedance is in ohms, so you add them like you would resistors, and your admittance is in terms of Siemens, so you add them how you would add conductances. So one way to do it is to put them into admittances and then just add them together like you would add conductances. So you could just add them, the parallel ones in series. And then once you have both of your conductances, so you could make this into Y,
Y. Y1, Y2.
Y1 and Y2. And then you would add those two like you would add them in parallel. But that's how Russell usually solves it in his solutions. I personally like using impedances more. And how,
Well, because whenever if you were to use admittances, you would have to like convert a lot more, right?
Mhm.
Yeah, because you have to go from it. Or well, I guess you can just start off with admittance. But like usually I like start with impedance because I forget it.
Yeah.
And then I change to admittance.
Impedance is nice.
And then I change back to impedance.
I like impedance, so we'll do impedance. And I highly recommend making a sheet, like a reference sheet. It's open book, open notes, but I made like a study sheet that had all of the conversions, that had like a little nice matrix for Thevenins and
You
like,
still have it?
Yeah.
Yeah.
So just, you send to us?
Yeah, do that on Discord. Or.
yeah, sure. It has like some extra stuff, but I can pull it up.
So Chris, something I've been meaning to ask him. He said as long as it's on your laptop's on airplane mode, you can use it. Can I use multisim as long as my computer's on airplane mode? Or is that cheating?
Whoa.
Please don't.
Why did you?
I was going to on the first exam and then I forgot to ask, and so I didn't. But
Yeah, please don't.
just don't do it.
Yeah.
Okay.
Yeah.
So you can use, what you can do is if you want, you can use MATLAB, because some people who don't have the calculators will do Kramer's rule on MATLAB.
Okay.
Or Desmos, which is, I don't like the formatting on there. And if you want to know how to do it, I'm not the person to ask. But yeah, don't use like, a solver on the exam.
Circuit
Yeah,
simulator, yeah.
yeah. So it would also, well, I bet you could probably put it all in time, but then you would have zero work and I wouldn't be able to really.
That's very true.
Yeah.
Okay, so you're probably getting no credit for it.
Well, what
Yeah.
if you can just use it to check your hand?
That's
You
more
won't
what I
have
was
enough
asking.
time.
That's more.
Yeah, you're not really gonna have time for that. And again, please don't.
What if you're done where you're working, you have extra time, then?
Also,
Well, no, that's my thing.
She already says okay.
Yeah, I mean, if I'm gonna give you a proper answer.
I mean, if you're gonna,
I've used it on home.
I've got like one or two.
You won't-
problems.
you won't be able to find some of it because it'll be running.
Yeah.
But also if you've got that much fucking confidence that you'll have that much time while you even attending the review.
Yeah, pretty much.
All right, well,
Okay, what's your next
let's go ahead. Let's convert these and let's add them up. That, please don't take that as a challenge. I was gonna say that. No. So,
I'll show you, yeah, I'll show you all.
we're gonna call this
Back to.
one.
Takes the next breath.
So ZC, what is our ZC and our ZL gonna be?
Wait, this is an impedance, right? Not, yeah.
Correct. We're doing,
So
we settled on doing impedances.
the impedance of the capacitor is going to be negative 200I. And then your impedance,
Pretty fast.
negative 200I. Or just,
Ah,
I got, negative 2 times 10 to the negative 8. That would make no sense.
you have what?
1/500 times 10, negative 6. That's 2. I'm sorry. Well, yeah, it'd be 500 times 10 times 10 to the negative 6. So technically times 10 to the negative 8.
why are you doing times 10?
Sorry?
Why are you doing time? Oh,
Like the same.
It is 200.
Times
200.
negative 6. 200. I got 200.
It is 200. Yeah.
Negative 200.
Negative
200 and.
Oh, I forgot that the number one high, but honestly, that wouldn't make a difference.
so this is what it's gonna be over here, right? It's gonna be 1 over, and I'll do it on my calculator.
It's 200.
I don't think that. You get a positive or negative?
For the capacitors?
Yeah. You should get a
Well,
negative.
you should get a negative.
Yes.
Well, it's 200 over I, which gives you negative 200, or J, sorry.
Got it. Yeah.
I got negative 200 J.
By the way, by convention, does J come before the numbers or after the numbers?
Or, yeah, it doesn't matter.
Doesn't?
Convention
It doesn't matter, because on some of the.
before. I always end up accidentally writing it after, so I don't
mean,
really
that's-
care.
Sweet.
It looks so ugly.
What?
It looks so.
Well, you take.
Yeah, it doesn't look right.
Okay.
Yeah, they bothered me, it actually,
But
like J too.
I got scared because I was putting it.
Oh, yeah, I can put it back.
It can be before or after. I think technically it's supposed to be before, but to each their own in my mind. If somebody else is like, I'm gonna count points off, then that sucks, but you gotta do what they say. Hua indeed. So then ZL, what's our ZL gonna be?
J one.
Yeah.
J100. All right, so now we're gonna do our Z1 is equal to R1 in parallel with CL.
PCBs are cringe.
I gave it.
R2 in parallel with
Yo,
He seems like the.
What'd you get going?
CL is omega L, right? So,
Yeah.
yeah, never mind.
Scaring me, man.
all right, so and for people who are watching this review later, if you're wondering how to do your your imaginary number, you can't just type the letter I on the keypad. You have to go to the little pi symbol on the bottom of your calculator and then hit your I there. Now, if you find that really annoying, what you can do is you can map your I to the imaginary I if you just want to put it on the keypad. Which there's this little dot equals. That's terrible. Dot equals.
Oh, the big control.
Mm-hmm. It's like the top right. So if you want to hit like I from the keypad is equal to your imaginary I.
Oh, I'm good.
That's pretty cool.
I'm good.
That's actually really good.
Yeah.
But it won't last forever. Like you have to do it each time you make a new document.
Yeah, but why would you make a new document?
Well, I mean, just in case, things happen.
That's fair.
And
But
personally, I make new documents all the time. I don't like saying.
that's fair. It's just some of the things that I've seen people do. It's interesting. And that's how you can always put variables in too. So if you think that you have your impedance as a really ugly, gross number and you don't want to keep typing it in, you can just do Z equal to, and then your value.
Okay, so can I use that instead of the define function? So instead of having to go to the menu, get define and set it up that way, I can just say this equals that and then it would do it. That is really cool.
That's using for the almost door function, control and.
So you do it like that. So now every time I type I,
That's more temporary.
Is that,
wow, thanks.
but the thing you just did is that permanent?
Oh, okay, gotcha.
Mhm.
I'll keep that for a while.
Yeah, so that's a nice little thing, but what does your Z1, have y'all solved for Z1 and Z2?
So for Z2.
So for Z.
What you got?
Oh, Z1, I got 40 plus J and 80 for including phrases. Damn, I did something wrong.
I got like 2,000.
2000. I got 89 and 44. My whole equation for Z1 is parentheses, 1/200 plus 1/, J 100, close parentheses to the -1. That's usually how we get the parallel, and they come out pretty good. But I got 40 plus J for Z1. It's just 200 plus 100.
It's 200 ohms, right?
Yeah, it's 200.
200 ohms?
Yeah.
Oh, we all get people.
200.
It's 2,000.
Oh, I don't think they're gonna.
It's 2,000.
Top one.
No, it's
It isn't.
So I got 40 plus
It's like
80J
Noise.
for
Oh, yeah.
Z.
You just treat it as a history.
So every time I'm gonna write something, I wanna see that I have to.
All right.
And then Z2 is 80 minus 40J.
Which I hate doing.
Mm-hmm.
Yeah, 40 minus EJ.
Well, I just, we established was the answer. I got a fuzzy one.
No, we're not there yet.
Did you by chance, have a negative on the denominator of? Would you have actually party? It should be fine.
I think 40 minus 80.
Bingo. Like that. It's just a parallel.
There's some. I just want to like make sure that we don't solve the whole problem with the wrong impedances. So what'd y'all get?
For Z1, yeah.
For Z1
Maybe less question mark.
and then Z2?
80 minus 40 J 40.
Yeah.
Sweet.
Cool. So you said 80 minus J40, and what was the other one? 40 plus?
Plus J. And for this part, we just go with the voltage divider, right?
Exactly.
And on the numerator, it's for voltage dividers with impedances. It is the one that we want.
Yes.
Cool. Oh, I got you.
So what that was so your Vx, so the voltage that you want, is equal to your Z or your R X plus Z1 plus Z2 plus ZX times V total. Which is equal to your, we want Z2 because, and we said this earlier, but I want to emphasize this because these two right here, R2 and RC are in parallel. R2 and C are in parallel, so the voltage across them is the exact same. So when you condense them down, you don't have to separate them out again. So the voltage over that is going to be the same still. So once you do the voltage division, that is VC. So we have
Okay. Yeah. I think she's just giving an example. Oh. But if it was, it's weirder to do admittances with voltage dividers, right? It's more work.
yes,
And it's the opposite for current
Correct.
divider.
yes.
Curious, that little thing that you showed me with that, the, almost was the equal sign thing, but it's like not equal sign. It was just like saved me so much time.
It's
I didn't know you could do that. I thought you had to go to the define function every time, but it's literally just.
that's what I did.
Yeah, and like it takes me like 5 minutes to
I think
like get everything in.
it's also day like 3 with this calculator stuff. Thanks.
Yeah, no, the calculators are such a good tool. And like I said at the end, I'll probably do a separate recording and do just like a useful things.
Yeah, that'd be awesome.
Yeah, please, I'm too down with it.
Yeah.
Okay, so if we're going in admittance, we would have to treat them as Siemens, right?
If it was in admittance, everything would be in the unit of Siemens. And you would have to
Yeah.
combine them using how you do with conductances.
Angle 135.
To use those in super function designer.
I did try to look up the concept between.
5 and 5.
Curious this space.
What'd y'all get? We still doing it?
No, I stopped for a second. Well, so for my rectangular, I got 5 plus 5J. And then
Oh.
if I,
Yeah, 5 plus 5J.
What did I do wrong?
That's
and then let's see, that's,
that's pretty much what you have. AZ, you were trying to buy versus 40J, what's it?
And then, 2, no,
What did I do? So.
5 square roots of 2 for,
What'd you get? 5 plus 5J?
yes.
and 5 square roots of 2 for your,
Negative 80 minus 240.
That's
Okay,
great.
so you're going to.
Yeah, so for polar, I also got 5 root
So that's.
2, and then the angle is at 45 degrees.
So. It's, you know, just.
So-
Stuff like that. So that's why you do like this. Take this.
Wait.
Voltage divider, just 2 components.
5 and negative 5, right?
Yeah. Whole lot of voltage.
Yeah, I got 5 minus 5J.
Yeah, that's what I got. I got five.
That's a negative 45.
It should
right?
be 5 minus 5J, J5. 5J, same thing.
Yeah, negative 45.
Okay.
And to put like in the TI inspire, to put that 5 minus 5i into. Go with that phase angle. You just click it and you go to menu.
I was doing an Argand diagram, just a ballpark the angle.
To convert it to polar,
Yeah, like is it a menu
mm-hmm.
and then is it gonna be actions?
Number, it's so menu, number, which is 2. Complex number tools, which is 9. And convert to polar is 6. So if you're a number person, it's 2, 9, 6. And if you want, you can also, if you always want your calculator to give you polar answers in settings, you can do document settings. And,
Will each one, would any one be correct? Is it, they say something in class, so he wants the answers at all 3 of them or no?
Well, he'll tell you.
he'll tell you, I would write, if it asks for it in time domain, it's gonna be the most helpful for it to be in polar, right?
Yeah.
But in things like this, the answer is a lot prettier and rectangular. So, because did everybody get 5 minus 5J? And people who didn't, what's up?
Alright.
Jay, I'm sorry.
Supposed to be 5 minus 5J?
Mhm.
On that formula sheet up there, it says VX.
Oh, I see what I did.
Yeah, that's good.
That's the VX equal to ZY. Or ZX. On the
Yeah.
Here,
top right, this, yeah.
that's ZX. That's ZX. Yeah, so all that means, as I was trying to say, the voltage for the one you want is the impedance of the one you want plus the total impedance. So the reason I put 1, 2 plus X is to make sure that you know to add in the one that you want on the bottom too. It's just a formula. But yeah. Which is equal to, and what did we say it was equal to in polar? Can you give it to me in decimal?
In decimal, 7.07.
You care about the square root or no?
If it's in time domain, I would want decimal.
Okay.
7.07 negative 45, right? So how do we put a answer that is in polar back into the time domain?
That way to the front, that's your, voltage key.
It's 7.07 is the magnitude, right?
Yeah.
And the angle we get is the phase angle. And the inside the brackets of the sine and cosine.
Yep.
And then what is it? The radiance is just given from the problem.
Yep.
So this, it was cosine, right?
It was sine. Does that change things?
And it's-
So
The EG was in sine.
They were both inside.
They're both.
Yeah, they're both in sine. Now, if you do,
It does, yes.
yeah, if you have it given in cosine, then you have to 90 it.
mhm,
Now,
exactly.
another question.
Yes.
Since we're in sine, right? We want to keep it in sine, right?
And that's what he asked for. So
Correct. Like, if he didn't give us like an equation that he wanted to have us solve for, it's just best to keep it in terms of whatever was given. Like if it was a cosine, keep it in cosine, if it was a sine, keep it in sine.
typically it's going to be in cosine. If he gives it to you in sine, he'll either specify if he wants it in sine or cosine. So
And then the process is just the exact same. Don't matter if it's in sine or cosine, it's sine.
90 and cosine.
Correct. But I was just saying, like this, we use sine, we normally see cosine, we use the exact same process.
Yeah,
Now, at this point, would it be better or worse, or doesn't really matter to use the square root, because in the assignment he gave us, something was square root. Oh, yeah, his son.
we just had a whole conversation about it
Yeah.
and I still wrote it wrong.
Did what I asked. Like, does it matter if we need the square root or not? Like, this in this one, because on the homework sets, it had square roots in it, so I didn't know if that was just aesthetic or better or not.
That's fine.
Really?
It's aesthetic. It's whatever you prefer. He puts it, his answer, he has it in sine with a decimal. That's what he did. But like you said, he'll go back and forth. So. So any questions, comments, concerns?
We're still doing that name.
Yes. Just before I move on to anybody. Like we said. If there's no. If you have your omega t, so your 500 t, and there's nothing else, like we said, your phase angle is 0. So it's just the amplitude. And then. Do y'all know, I'll go over this too later, but quickly, I want to show y'all how to put phase angle in your calculator. So, the way that I do it is, with the little book sign. And then number 4 has every symbol imaginable pretty much. And you just find the thing that looks like that. It's called angle. And you can just hit enter. And just remember, you also always need to like put parentheses around it because it kind of throws a hissy fit if you don't. Yes.
There's also another file, right? If you just place control book, it's like, it's second row, number 3.
Yeah.
Wait, control book.
That too.
I try to avoid the menus, but I get lost.
Choose the first one.
Once you close out of it, if you just hit the book, it'll automatically open back up to the 4th one. Yeah, so it either works, but that is very, very true. So yes, now, do we have any more complex admittance problem or questions?
100. Wait, never mind.
All right, let's do this fun name one. Doesn't this look fun, guys?
Oh, fine.
Go for it.
Well.
You want me to go back to it?
No. You have it like planned out already, so I was gonna say no. It looked like it's not possible, but could we do a 7 and so that way we can knock out 2 rooms at one time? Like a Thevenin's and a name,
Um,
because Thevenin uses name, right?
Well, but
Like,
at
no,
the same time, you know that he's gonna have Norton's on it.
Oh, there's not gonna be a Thevenin on the, oh, okay, then never mind.
no, yeah, it's
That
gonna
was a-
be a name. It's gonna be a Norton's. It's gonna be a combinations.
Okay.
and It's gonna be a complex events. I promise.
Okay, thank you.
No problem. So.
Well,
No.
that's all I was asking, if we could see. Suck it. you know.
Well, then,
Dude, I hate if I get so.
Well, then let's do the problem. Um. So. This is a good one. Oh yeah, sorry.
no, it's not. This is the third one.
This is a good one. What are you talking about? It is 5. This is why the calculator is really important. I know some people who did Kramer's rule, and Kramer's rule is really awful when you get to a 5 by 5. 5 by 5. But yeah, so we can see that there's a lovely 5 nodes. While y'all are writing down, you can go ahead and see this is going to need to transform. That was hideous.
What is transform?
The voltage sources, like dependent.
Mm-hmm. This and this, because name equals currents.
You say anything like. Alright, so just something like this and stuff like that.
Exactly. That was like the next thing I was gonna write down. So we have not lots. We have 2 variables. We have I7. Damn it. I8. I will let y'all finish writing down.
Sweet.
No, it's gonna be a good test though. Y'all are gonna be fine.
He said, no,
Have you seen it?
he said no hexagonals, he was like the next best thing. Bye. Hexagon thingy.
Well, so, but if you can do this, then you can do.
We got through it, you know.
What do you be doing?
Yeah, I will say this is, well, hard is like, a problem being hard is relative to what you're good at, but this one looks scarier than what you're gonna see.
You promise?
I promise.
Okay.
Well, I think so. Like, I think it looks scarier. Um, yeah, it's not a fun one, and I don't suggest, well, no, because I see everybody just trying to write it all down. It's not fun to like copy this down. What I was gonna say is, I really don't suggest redrawing anything like this on the test. So if
It'll be pretty easy to redraw. It will be time consuming.
it's a fight against time already. So what you're gonna want to do instead of redrawing the whole thing, if you can, if your brain can kind of skip some steps, which if it can't, take the time. It's better to have a right answer than to have It's better to have a right answer and half of a finished test than all of the test finished and all of them be wrong. So if you can, just take like the things I circled and just redraw them right on it, or draw it like next to it. Or for this one up here, draw it just down there where there is that extra part. If you need to redraw it though, just make sure you just take your time. Well, both take your time and just don't make mistakes.
Great.
Yeah, thanks for doing that.
I know that's incredibly unhelpful, but I saw it a couple times. Someone would redraw the circuit and they would copy one of the numbers down wrong on that.
You literally looking right at me, said that.
Was it you? I don't,
I'm sure it happened.
yeah, it did. But so maybe if you're looking, like after you redraw it, look at the numbers from the original circuit instead of the numbers that you redrew to just cut down on the errors. So I7, what's I7?
Gonna be your
B and three.
B and 3. Yeah.
G7 times V3. That sounds right. V3.
5, 4.
7, and remember that's because V2. There. There's a little, just, again, I promise I write it every time I write V equals IR just to see it.
Just getting the grease.
No, it helps me remember, and that's just how my brain works. So what's I8?
V5 times.
Minus B and 2.
Is it V and
But
5?
it's, yeah, G8 times V and 5 minus V and 2. That was a lot of words there. I mean, but
So it's G8 times VN5 minus VN2.
oh,
So why is it VN5 minus VN2? Why is
Because wherever current come from.
bingo?
You told me that a long time ago.
Yep. So why is it VN5 minus VN2 and not the other way around?
Because of the way the current
I don't know.
goes from high to low.
Exactly.
I don't know.
To reiterate, for the other people online, VN5 is the higher voltage because current is flowing out of it. So we're going to subtract VN2 from VN5 because we're assuming, based on the polarity of the current, that VN5 is the higher one, or bigger magnitude. But yes. So let's go ahead and go to our 5x5 matrix. Woohoo! All right.
Isn't this fun?
It's so much fun. I don't know what you're talking about.
By inspection.
So tell me what to write, y'all.
10.
Is it?
Yeah, it's 10.
You're
6? No, yeah.
5.
Where?
That's 5. It's G6 plus G5 plus G9 that equals 10. Yep.
that is next.
10. Okay.
Shrink.
What's next?
The one that is shared between V and 1 and 2 is 5, so it's a negative 5.
Shrink 5.
Nothing shared between V and 1 and V and 3. The one between V and 4 and V and 1 is 4, so negative 4. And I'm just now seeing, well, no, nothing between V and 1 and V and 5.
All right.
That's the other thing. I feel like it's trickier to see what's going in and out of nodes rather than meshes.
Yeah.
It is, and what you need to remember is you have to go all the way down the branch, right? So it's kind of weird, and I understand the confusion. But if we think about kind of what we were talking about earlier, about how when things are in series, they share the same current. And when things are in parallel, they share the same voltage. So the whole branch, no matter what, like from the node to the other node, that voltage drop applies to all of the elements on that branch. So just because there's two elements on one branch doesn't mean that you can only look at the first thing you encounter. So because we're looking at them with respect to the nodes that Russell has given us, those are what, like, sorry. All of these node voltages are measured with respect to ground and the other nodes. So if we're looking at VN4, for example, we can look at it with respect to VN1. But that means that we have to look at everything from the path of VN4 to VN1. So even though this right here isn't directly touching VN4, it is still connected to it through that line from VN4 to VN1. That was a really long and convoluted way of explaining it. Did that make any
So,
sense?
You probably just said something that I was wondering about. So like, even though that there's a voltage source in between, or in between the conductor and, so I say like VN1, that is, yeah, there's a voltage source in the way of the conductor that's between VN4 and VN1. It's still shared between the two nodes.
And we also need to convert it
Totally,
anyway.
I need that too, yeah, but, okay, cool.
VN1 to VN3, from VN1 to VN3, would G7 not be included?
VN1 to VN3. No.
We're connected.
No, because this is where he just says crossovers.
Yeah.
It means that this is kind of like that.
So yeah, he says crossovers, just so we know there's no node, right?
Yeah.
That-
Yeah. It was touching me, it's put you on there, like.
There was a node that.
Oh, if they were touching, this whole circuit would be insanely crazy. Well, not insanely crazy, but obviously be different than what we're doing.
If they were touching, would you just make that a node too?
Yeah. If they were touching, it would just be a node.
Never mind. That would be difficult.
Facts.
Yeah.
The center, VN2 and VN4 would be touching, right? Or would that independent source still be in the way?
The sources aren't in the way.
If there's a node in the middle, you treat that as like one little node, so no matter what, VN2 and VN4 are not touching. Okay. You're looking at it like, basically look at it like it's a line, like VN2, just see where it goes.
Like if it's in
Yeah.
hands, kind of.
Yeah.
They're literally touching hands.
Because you have to basically go in a straight line.
Okay.
Any direction, because for VN2 and VN4, you have to go boom, boom, which is not a straight line, so they're happening.
Oh, so.
G8 is not connected to VN.
Yeah.
So I have one
You see with VN3.
G8 is not
straight
connected
line.
to
Yeah.
VN.
VN2, VN5, straight line.
Yeah.
But VN4 and VN2.
No, G and VN5 are connected.
Oh, if they're not in a line, then, okay, it's like I'm wires, those on each other.
See this line? It's confusing, I know. But this line right here connects these two. So, yeah. I know, really confusing. And we need to convert this and this first, actually, before we do the matrices. So that's on me. I mean, it doesn't technically change it, but we should do it anyway. So, what I'm gonna do is I'm gonna draw over it. Um,
When you kind of, going forward a little
Okay,
bit,
yeah.
when you transform EG4 into a current source, it's going into VN5, but not going out of anywhere. Technically, it's going out of ground, but in the whole VN spaces, it's not going out of anything. That makes sense?
Yeah, that's right.
mhm. Sorry, I'm annoyed. I'm trying to get a white and it's not working. But, so let's go ahead and convert this. So we're trying to convert it to a current source in parallel with the conductance. What's it gonna be?
Just like,
Mm-hmm.
it's like. It's just right on, right? Like,
Yeah,
well, no, you can still mark it up, like just.
Yeah, I mean, you can just keep your resistance and draw lines to the voltage source.
that's a better idea.
Sure.
I think at this point, most of us know what you're trying to do.
Right.
It's just better to see those.
I know. So which way is the current source gonna be going?
Upwards
Yeah, up.
into,
And then you can just cross out 3 volts.
Maybe upside down, you got it.
What you say?
I just said take the V and flip it.
Yeah,
You got it.
You got an A. Yeah. Might have to add a little set, but.
Yeah, don't worry about that.
Yeah, pretend like that just goes away. We're just gonna do that. Good
There
enough.
we go. Yeah, that's.
Good enough.
Looks great. That sounded.
Yeah, that
sarcastic.
Okay. What's the other one gonna be?
What do you mean? Oh, it's gonna be G9 times RMI7, right? Yes, no? Yeah. Yep. Sweet.
It'll be a current source going down.
Did I have it going down? I did have it going down, thank God.
It is going down.
Correct. Yeah, because conductance is like 1 over resistance.
Yeah.
So it's like you're dividing by resistance.
Mhm.
Oh, that's nice. That works out.
Doesn't matter.
And then it's 4 times RMI7. That's what y'all said, right?
3 times that sound.
What? What?
RM.75 everywhere.
Oh, okay, yeah, I was like, what?
Sorry, my bad.
Skippy said that, right?
Yeah.
Here you are good. And so yeah, let's do the resistive matrix now. We have our sources that are
You can just copy that row to a column.
good enough. Yep.
I'm even using terminology now. I semi know myself.
I am very proud of you. Sorry, that sounded sarcastic.
You said everything you just said. Right. Negative? Don't worry, no. If I'm talking to you. It's not. I like that.
Okay, what's the next? What's 2, 2?
-5, 8, -2, 0.
8,
Yeah, 8,
8, -2.
0, 1,
-1.
-1, sorry.
And then you copy that.
All right, 3, 3.
5.
5.
Right?
Oh, yeah, you got that.
Negative. You're always gonna shoot.
-1.
-1, 0. -1, 0.
So.
Then there's a 9
9,
and -4.
-4. So,
That's what I got.
Yeah.
I just didn't hear you. -4, -4.
And then the last one's 8.
Sounds good. All right, now the fun one. Let's just do it. Let's do it all, then we'll separate it out.
Oh, G9, RM, I7. And it's positive.
G9? Huh?
Yeah, G9.
Yeah.
Oh,
I'm
okay.
just giving it as like, I'm giving it letters, not numbers yet.
Okay, do y'all want to do
I would,
for,
It's easier for me to see it. But
yeah, I'd rather just write out the, not the numbers, the,
The letters,
yes, the symbolic references.
okay, cool. Cool.
you pulled out the term.
Oh, yeah.
G9 times, what was it?
RM, I7.
7 plus
Oh, it's not.
minus, oh, that's it? Cool. I'm not looking at it.
Yeah. well, fair.
This is all I can see right now.
That was more of a right to the room. A question to give about if you want it.
No, it's all good.
Oh, the next one, it's negative JD. But it's going out of the area.
All right.
And then it's positive JD1 on the third thing. It's minus alpha I8.
For the fourth one or on that same?
Like that same.
Minus alpha. 8.
And it's alpha I8 for the next bracket. Staying in the same bracket. Minus the G9 RM I7. That's it for that one, and then just JD4 on the bottom.
Heard also not that about
All right.
It was impedance, right? Impedance.
This is
No,
This
I
is-
know that. It was a term. How do you say it again?
impedance.
Impedance. I said impedance with Dr. Russell.
Did he say anything?
No, he just kept on going.
Maybe he thought it was like an accident.
Yeah.
All right. So numbers and node voltages.
I7, which is 3 times VN3 minus, oh, no, just 3 times VN3. The top one. And then negative JG is just -1. That's 1 minus alpha, which is 2 times I8, which is, so it's 2 VN5 minus 2 VN2.
I think we already did this. Oh, wait,
So we're just writing out the numbers.
Right.
Copy and paste the 2 VN5 minus VN2 out the negative. And then take what's in the top and add a negative.
And what's JG4?
Oh, 9.
Alrighty. Now separate it out. Do that down here.
I don't. For G9 times RM times I7, I got 3 VN3.
I got 63.
I got 6 as well, yeah.
Yeah,
Oh,
because
yeah.
I7 it becomes, when you actually add the numbers in it, it's 2 V and 3. And so then you add, multiply the G9 R is
yeah.
I7.
Yep, that's my fault.
Are you good?
It's on the happening.
Oh, you're punishing just 10 minutes of silence.
He's been very quiet this session.
Yeah. This session, because I don't think he's writing stuff.
Hold on.
Well, that day you were disrespecting Grace, I think.
Oh, that day.
Where she just came.
Okay, back to the review. We're doing something here.
You're giving him PTSD.
Is everybody happy with this?
Yeah.
Okay, now
Isn't the second one supposed to be positive?
You right. Do what Russell says. It was a test.
Yeah.
So this one just has VN3, so it's 0, 0, 6, 0, 0. Right? Not a rhetorical, I'm not looking at it.
What, yes? Yes.
Yeah.
Yes.
Okay,
Straight line 0.
sweet. Next line.
0, 2, -2.
The next one.
Right.
0, -2.
And then 0,
Hmm?
0,
Oh,
and then 2.
2.
oh, the -3.
I thought it was,
I think it's full.
is it flip? Yeah, I got
What's
flipped
up?
on mine. I got 0, +2, and then -2.
Yeah.
Yeah,
Yeah.
that's right.
But it's the other way around, or it's how you have it.
Sorry,
I'll just give 10 minutes of silence again.
Oh, yeah.
I was reading it wrong. I was doing the fourth one.
We're not gonna get a 5x5 matrix on the test, are we, Chris?
And it's not like you're doing it by hand, you put it in the computer.
I don't remember.
We're doing it back to.
That's not a.
It's at least 4.
Sorry, Papa.
All right, everybody. I'm gonna do what Alex had said of just the VN.
Wait,
That's okay with it?
Yeah, I didn't even see that.
Yeah.
I was like, no.
Right.
Alex left, that's why I started talking.
I think I have it.
I didn't need to say anything while Alex was here.
I thought
All
because you were
right.
scared of him or something. That's what I thought.
yeah, I'm scared. I'm scared.
Scared of him.
Technically, all
Scared of
right.
his intention. That's what I'm scared.
So like we did earlier, these two subtracted from each other.
Negative.
Wait, literally, guys, this much blank space, that's it.
Two.
You know, if we didn't have name or name, we'd be writing a lot more.
That's actually very true.
Yeah.
That point there.
We'd be in a lot of pain by that point. Like physical hand cramp pain.
Yeah, I agree with that.
I'm gonna just go ahead, try to get this down so we can talk some more after.
You know, apparently Dr. Turner used to teach, circuits. And, I was like, you didn't name a name with defense circuits? He's like, nah. I'm like, I can't even bag you. I will have to agree.
Mm-hmm.
Don't
Hey,
think they
be
teach that in
thankful.
Austin still, do they?
Be thankful.
Teach that in Austin.
Be thankful.
Like UT Austin, I don't think they teach that in Austin.
Because
No, they don't.
it sounds like
They
basically,
don't teach in Austin still.
it sounds like Howard's like the only guy.
Oh.
That, and Howard, like, I was like, okay, you know, it's never.
Hey, that's why he's the GOAT.
Yeah.
That's why he's the GOAT.
How would you?
Oh my gosh.
I don't.
A lot of
I
Actually, I remember doing this in physics, and a 3x3 matrix was like double as long a process as this 5x5.
No,
So.
I don't wanna imagine physics.
Grace.
Yeah.
In the
Physics
decommit,
two.
Yeah.
Yeah, I mean,
where
You didn't do that yet?
row 1, column 3, I got 16 instead.
and I'm not gonna.
Which element? I
Row,
got her matrix as well. I got her matrix as well.
Okay.
So
row,
basically, you're just, you know, wrong. So.
Hey, sir.
Someone just dunk on Zach.
16?
where? On the second, when it got subtracted?
Jumps on.
Well, if you got something to say, you better be right. I'll not be scared.
Yeah.
So you-
Oh yeah, that was just like earlier whenever I asked like where our grades were, y'all started like shitting on me. I was just asking
That's
a
pretty
question.
normal by triple. Don't take it.
Anyway, but so
Yeah.
because it's G9 times R and I7.
next.
So I7 is 7.
Yesterday, I
3.
think.
So is in a 4 times 2 times.
Hey, are you gonna have a final review?
4
We-
is 3, and then
The
3
final's not
times.
gonna be too bad.
two is
You use name and names, literally everything. So once we got that, we're good.
Y7 is V3 times G7.
What's up?
G7 is 2,
And then
That's better.
and then
Imagine if we did a 5.
RM is 0.75
Wait, Grace,
times,
will we see in
Four.
circuits 1 or circuits 2, like? a
so 4
complex,
times
uh,
75 is 3,
Number.
and 3 times 2 is
matrix,
6.
Like 5 by 5.
oh, that's fine. Okay.
Yeah,
No, I multiplied by alpha. I didn't multiply by RM.
You good? We good?
I think so.
Arms 3.
Okay.
All right. See y'all people. Good luck on that.
Oh, arms 0.75, like you.
Okay. Now, all you gotta do is put it in the calculator.
this one. It's negative 1.
Did I not put a negative somewhere?
Negative 4 minus 0.
Alright, see you all Thursday.
Did I not write -6?
Yeah, I'll see you tonight.
Whoa!
For differential equations.
Sorry,
Differential equations.
I'm mistaken.
No, you're good.
Focus. Go head out of the gutter.
What?
Whoa. I thought Alex,
What type of conversation did that just?
I thought Alex,
Don't worry about it.
thought Alex left, guys. Come on.
Did y'all get an answer? Do I still have to take this in?
Alex left, but
Nobody has said anything yet.
Okay, it's gonna take me a half minute, hold up.
I just saw the Discord and I thought.
Just remember, something that's helpful is, whenever you're doing a matrix, you can always hit tab to go to the next one.
Yep.
Seriously?
Yes, so like if you wanna go from the next row down, you just hit tab. Tab.
Based with the live minutes.
You really don't.
We can also just press the button.
It's insane.
Yeah, but then whenever you like wanna go from like this one down,
Then you have to go, okay, but if you hit tab, it will just take you
Yeah.
back down. Oh, okay, great.
Can you scroll a little bit? I just want to see the matrix on the right side before you switch it over.
and I did the matrix on the bottom quickly. If I did it wrong, please let me know.
Well, I hope.
no, don't
It's
do
just
that.
such a time consuming.
Hmm?
You time consuming my whole life.
Give this to her,
Whole life?
Oscar. Give that to her. So that's 5's what I got. That's what I got.
What'd you get?
It was a lot of numbers. Hold on, she has it.
Is it like 1.6?
Yeah.
4, 5, and then 1.33, and then 0.75?
Yeah, that sounds right.
Also, you can, instead of doing to decimal, you can do control enter, right?
I didn't know that. Okay.
Yeah, I learned that today.
Good thing.
Yeah. So.
You
Yeah, so the little
Enter.
enter above has
That's
little
what I
squiggly lines, which is the approximate answer. Also, if you want your calculator to always do approximate mode, you can do that in settings. Right now, it's probably on auto, so if it thinks it should do approximate, then it'll do approximate, and if it thinks it should do exact, it'll do exact.
But you just made her do your work right now?
No, like.
You know the test, she's not gonna be able.
Oh, she's like working so hard.
No, he just did it the hard way. He like went into the menu and did convert to decimal.
Well, I memorized this menu 2-1.
Don't make it.
There you go.
I didn't realize, I didn't see the equal sign on the setting.
What'd y'all get?
Are you still in polar for that?
That's what I heard.
Maybe, yeah. Is that gonna affect it?
Huh?
Is that gonna affect it?
Yeah, you're still in polar.
That shouldn't change anything on this.
Unless you have.
Did you get an inverse tangent answer? Because if that's.
No, he did row reduced echelon form, so it
Oh,
shouldn't matter.
okay. Yeah.
You switch these two.
Wait, so what are we, so this problem?
It'd be -1. Oh, wait.
Oh, all of them?
Oh, wait, no.
We're just.
No, you're right.
What about the astro?
Check.
I just like cleared off.
I said.
-1,
Check.
0. -4.
Oh.
There it is.
1, 0, 4, 5.
I'm talking about the VNs.
Yeah.
It was wrong. That's what I'm saying.
There's also invested.
Oh, mine is wrong. 0, -1, 1, 0.
Weird.
Yeah, that's wrong.
Oh,
That's that's what I checked.
Sorry, Papa.
What you? 0.
Julia, what were the numbers?
1.64532, 1.33498, 0.75, sorry, 0.751232, 1.31773, 1.95074.
All right. These are in amps, right?
No.
Volts. Volts.
I try to play mind games.
Yes.
I don't like this. I have enough stress in my life.
Oh, I already. All right, so that concludes what pretty much what I had. Just remember capacitors are the opposite of resistors. So if you see two capacitors in series, add them like they're in parallel, etc. But I trust that y'all will get 25 points on that question. I trust y'all.
Like the last one where it's like root for infinity and 0, or is it just like plugging?
She's not gonna tell you.
Well, I mean, that's not cheating if she tells us, bro. It's just like.
That's just.
That is, all we need to know is.
There's nothing about infinity, because think about it with a capacitor, that would be
I feel like they were only include infinity when it comes to switches.
like capacitance has to do with like, derivatives and they're not, they're like exponential and whatnot. So
He's trying to get on the good side of grace, especially after what happened.
y'all.
You're trying to get on the good side after what happened.
All right, you know what, fine.
All right. So I'm gonna go ahead. I think I'm gonna record another thing after this for the calculator stuff. So I'm gonna go ahead and end this recording. Stop sharing my screen.
So you're gonna post it on Discord later tonight, the video?
Hold on.
Who's the video?
It's been.